Okay, we're on to question 5 from the DEB 2020 paper 1. So in question 5 it gives you this quadratic function and it says find the range of values for which this function is greater than 12. So when we look at this, I mean automatically you're going to think of, let's write it out like this, okay? So f of x is greater than 12, so x squared plus 2x plus 9 greater than 12. But what I want you to understand is this, is that this is some quadratic function that's u-shaped because of the positive x squared. If it was a negative x squared, it would be n-shaped. I'm a big fan of small sketches. So we look at a sketch of this quadratic function here, and we see here's f of x, some u-shaped function on some xy coordinate system. It essentially is asking you, where is this graph bigger than 12 on the y-axis? So if this was 12, the value of 12, let's draw a dotted line across. Okay? So what we actually want to know is, where is this function bigger than that line? Well, it's bigger than that line for all of these values up here, because this is where it's above the line, and it's also above the 12 line here. Now if we go down to see what it's looking for, that's going to be some x value there, and this is going to be some x value here. So here's x1 value and here's the x2 value. If it's bigger than 12 as it gets bigger here, that means for all the x values above this x2 values, it's bigger than 12. And if it gets bigger as it goes back this way, it's bigger than 12 for all the values below x1. So if you're ever unsure of how to finish this inequality, this sketch should help. But as I do it, it might explain it. So we can actually treat this like an equals. Why? Because I'm actually looking for these specific points. If you like, the points of intersection between the function f of x and the line y is equal to 12. So we could say this. What about x squared plus 2x plus 9 equals to 12? We want to find these intersection points. Well, it's a quadratic equation, and the only way we know how to solve quadratics is to bring everything to one side and set it equal to 0. So that's where x squared plus 2x plus 9 now minus 12 is equal to 0. X squared plus 2x plus 9 minus 12 minus 3 equals to 0. This is an easy enough problem. Let's factorize it, set it equal to 0. The factors of minus 3 that add up to plus 2, they're simply plus 3 and minus 1. That means when either x plus 3 is equal to 0, meaning x is equal to minus 3, or when x minus 1 is equal to 0, that's where x is equal to 1. So actually we can see our two x values are minus 3 and 1. Which ones are they? Well, obviously this is the minus 3 and this must be the 1. So it's actually clear now from looking at it, this function is bigger than 12 when the x2 value gets bigger than 1 and when the x1 value here gets smaller than minus 3. So it's bigger than 12 for all x values that are bigger than 1 but smaller than minus 3. And that's it. Now we're on to part 2 of A on question 5. So it says find the set of values for a k when f of x is equal to some k of x and it has no real roots. This is a discriminant case. Now to remind you of discriminant, if you look at the minus b formula, the part under the square root b squared minus 4ac is known as the discriminant. Now there's 3 cases for the discriminant. Let's look at case A. If the discriminant b squared minus 4ac is less than 0, then you have no real roots, which is what we're looking for here. But the other 2 cases are if it was equal to 0, you'd only have 1 real root. But if it was greater than 0, you'd have 2 real roots. So we're looking for no real roots, or imaginary roots. So what we want to know is, when is this stuff, when it's equal to k of x, going to have a discriminant of less than 0? So let's actually set this up first. So f of x equal to some k of x. So that's x squared plus 2x plus 9 equal to some k of x. So again, this is a quadratic equation and we're going to try and solve it for the discriminant, but we can't solve it unless we set it equal to 0 here first for the minus b formula. So let's bring over the k of x term. So x squared plus 2x. Now this guy comes over, becomes minus k of x, and we still have a plus 9 equals to 0. Now if we actually want to write this and set it out so we can find an a, b and c for our discriminant case. So let's kind of tidy up the middle a little bit. So let's say this x squared plus 2 minus k with an x. Now we can clearly see the coefficient with x comes together as a 2 minus k, and you have to group them like that so you can see what our coefficient is of x. Now, remember, for our discriminant, we are only looking for the b squared minus 4ac part to be less than 0. So what's our a, b and c here? Well, in this, our a is our coefficient of x squared, as always, which is 1. Our b is now our coefficient of x, which is 2 minus k. And our c is the constant on its own, which is going to be 9. So setting this up for discriminant case, we'll write it as is there. So b squared, what's that? So that's 2 minus k to be squared, that's our b squared, minus 4 times a, which is 1, times c, which is 9. And this stuff has to be less than 0. So squaring out these brackets, I'm going to get 4 minus 4k plus k squared. And then minus 4 times 9 is a minus 36, less than 0. So I'm down to here there now. So when I look at this, I can say, alright, maybe I can tidy this up a small bit. So I'll bring k squared to the front, and I'll put my k next. And a 4 and a minus 36, that's going to be a minus 32. Yeah, less than 0. Now, if you remember the first part, even though this equation in case is still a quadratic equation, I want to know when this quadratic equation is less than 0. What shape is this quadratic equation? Well, it's a positive squared, or our coefficient where our squared is positive. That means it's a positive happy face graph, so it looks something like this. Okay, so there's our y, so it looks like that. Now, when I actually say, where is this less than 0, what I mean is, where does this dip below y is equal to 0 line? So actually everywhere in here. So what I'm going to do is this. Because I want to know where it's less than 0, where it's underneath the x-axis, if you like, I want to find these 2 points here. What do we call these 2 points? Well, we call these the roots. How do you solve for roots? Well, you factorize it. So that's a k, that's a k. And the factors of 32 that are going to add up to minus 4, it's going to be minus 8 and a plus 4, which means the factors are k is equal to 8 or k is equal to minus 4. Now when we look at our graph here, it's quite clear that this is our minus 4 and this must be our positive root, which is 8. So actually, if we look at what I've coloured in red here, that's the part of the graph we want to know. This equation's true when the values of k are between minus 4 and 8. So the range of values are going to be k must be less than 8 but greater than minus 4. That's it. Now on to the last part of question 5, which is a simultaneous equation, and you can bet your life you're going to get a simultaneous equation in your Leaving Cert exam. We always do. We're very much used to 3 variable simultaneous equations in Leaving Cert higher level, but since this is just a 2 variable one, they've tried to make it a little bit more tricky, and it looks like this, which is a bit messy looking. So there's a couple of ways to do it. The way I'm going to go with is this. I'm going to use a substitution, and I'm going to say, I'm going to let a equals to, or maybe small a equals to 1 over x. I'm going to let a small b equals to 1 over y. Now I can actually, I always label my simultaneous equations a and b and c if you have 3. So actually by doing this, remember, 4 over x is essentially 4 multiplied by 1 over x. Similarly, 3 over y is same as 3 times 1 over y. So if you see that by doing this substitution here, I can actually say 4 times 4 over x is essentially 4 times a. 3 over y essentially 3 times b equals to minus 5. So I've rewritten a new a here with a substitution. I have to go back at the end and change back to substitution, so you can't forget that, right? So, and I'll actually need to remember this little key here to do that. Same thing over here. B now ends up being 2 times 2 over y, which is 2 times 1 over y, which is now 2 times b. And then we have 3 over x, which is minus 3 times now a for the 1 over x, and that's equal to minus 19 over 4. And let's get rid of this fraction by multiplying across the whole thing by 4, giving us 8b minus 12a equals to minus 19. So this is the whole thing multiplied by 4. Okay, now I have my 2 equations I'm going to use. So I have a 4a and a 3b. So if I write this one here underneath that one there, I'll make sure to put the 12a first. And then I'll have my 8b. I'll have my minus 19. So a regular two variable simultaneous equation, what I do, it kind of looks like I should multiply this one by 3. If I do that, I'll get a positive 12a there. So let's write the whole thing here again, multiplied by 3. So that's 12a plus 9b equals to minus 15. We'll write our other guy underneath it again. 12a plus 8b equals to minus 19. Adding these, they cancel. 9 and 8, 17b. 2 of these minus 34. That means b is equal to minus 34 over 17, meaning b is equal to minus 2, I think. Yeah. So b is equal to minus 2. Now what about a? Well, we can take any of the original equations, any of these equations. So let's take this original equation here. So where we have 4a plus 3b is equal to minus 5. Now let's replace our b by minus 2. 4a plus 3 times minus 2 is equal to minus 5. 4a minus 6 is equal to minus 5. 4a, when this guy comes across, comes positive, is equal to minus 5 plus 6, which is 1. A must be equal to a quarter. Okay, so we have our a is equal to a quarter and our b is equal to 2, but we must circle back because we're looking for x and y's, not a's and b's. So we said from the very start here, from our substitution, that a is equal to 1 over x, but we said a is equal to a quarter, so that's 1 quarter is equal to 1 over x. Well, if that's true, then that implies that x must be equal to 4. The only way 1 over 4 can be equal to 1 over something is if it's 1 over 4 again, so the x part underneath must match the underneath part there. So we know x is equal to 4. Similarly, we said b was equal to 1 over y, and we figured b to be minus 2, so minus 2 is equal to 1 over y. Again, a bit of cross multiplication. I know I say that word a lot and we don't really teach it, but y is going to take the place of minus 2. They're going to switch places. So y is going to be equal to 1 over minus 2, which effectively is minus 1/2. So that's what my y is. That's what my x is. That's it.